Welcome to the hands-on workshop, Performance Optimization for Intel Xeon Phi processors. This is episode 6. I'm Andrei Vladimirov with Colfax International. This episode begins part 2 of the workshop, where I will run several hands-on demonstrations of performance optimization on Intel Xeon Phi processors. In this video, I will demonstrate memory bandwidth optimization, and if something doesn't sound familiar, you can revisit episode number 4, where I talk about memory organization in Xeon Phi and about the high bandwidth memory. So let's begin. If you have a bootable Intel Xeon Phi processor, you have access to two types of memory: the regular on-platform memory based on DDR4 and the on-package high bandwidth memory based on MCDRAM. MCDRAM is very interesting to applications that require high memory bandwidth because you can expect over 400 gigabytes per second of streaming bandwidth from MCDRAM. But it takes some care to achieve that bandwidth. I will demonstrate what considerations you have to keep in mind, and I will do it by compiling and running the industry standard tool for memory bandwidth measurement, the Stream Benchmark. You will see that out of the box, the Stream Benchmark on a Knights Landing processor-based system doesn't perform as you want it to, and I will show what you need to do to get it running faster. The same procedures will likely apply to your own code that is sensitive to memory bandwidth. You can obtain the Stream Benchmark from Dr. John McAlpin's website, and this is the URL. So let's see what it looks like. The site looks like this, and under source code directory you will find stream.c. So I will copy the location of this link, and then I will switch my view so that I can run the hands-on exercises on a server with a Knights Landing processor. So first let me download the Stream Benchmark while I have the URL in my buffer. And here it is. Before I start compiling and running, let's see what I have in this system. So this is one of the systems from dap.xeonphi.com. It has 64 cores clocked at 1.3 gigahertz. This is the Intel Xeon Phi 7210 processor based on the Knights Landing architecture. Let's see what the memory looks like. There is a utility from Intel that can help me with this, and I see that my high bandwidth memory is configured in the flat mode. You can refer to session 4, to episode 4 for more information about memory modes. And I have 96 gigabytes of on-platform memory and 16 gigabytes of on-package memory. So this is my MCDRAM. Because I have the flat memory topology, I can run NUMA-CTL-H, and it will show me the NUMA nodes in my system. I have two nodes. One node, number 0, contains all of my CPUs from 0 through to 155. And local to this NUMA node is the DDR4 memory. So my processor has direct access to on-platform memory, no surprise here. There's also node 1, which has no CPUs, but 16 gigabytes of RAM, and this is the node with the high bandwidth memory. So let's see what it takes to compile and run the Stream Benchmark on this machine. we will be using the Intel C compiler. And I can compile the file stream.c, and I can direct output into the executable called stream. Out of box, compilation will fail because stream is a parallel code. It uses OpenMP for threading, and out of box the Intel C compiler does not understand OpenMP pragmas, so it is simple to fix. I will enable OpenMP support like this: ICC q OpenMP, output file is stream, and then stream.c is the source code. Okay, it compiled, and now I can run. First, let's run in the DDR4 memory, which is the on-platform memory, like this. I just run the executable. The stream benchmark reports 4 numbers for 4 tests that it does: copy, scale, add, and triad. It will be difficult for us to keep track of 4 numbers, so let's just keep track of one, of the triad test, which has some arithmetics on top of just memory access. Here performance is reported in megabytes per second, and I will record performance in gigabytes per second. I like to run the stream benchmark several times just to make sure that there is no huge variability in my results. It looks like most of the time I'm getting around 49 or 50 gigabytes per second. I will create a log for this. So out of the box, in on-platform memory, gives me 50 gigabytes per second. Now let's see what I get in the on-package memory. In on-package high bandwidth memory, which is the MCD RAM, I can put the entire application there, and if this command doesn't sound familiar, then revisit session number 4. So here it is running, and the triad test gives me 289, and if I run several times I will see the variability, well, between 265 and 290. So I'm not happy with this variability, but I will record what I get, something like 280 gigabytes per second. So not satisfactory, because I was expecting over 400 gigabytes per second. So what could be the reason for that? One problem that we need to clearly fix as soon as possible is that we need to tell the compiler to tune the code for Xeon Phi. We had a command like this. Now let's add one more argument to it. -x mic AVX512. If this doesn't sound familiar, revisit session 3. And now let's repeat the tests. Stream in on-platform memory. I will run several times. Gives me 65, 68 gigabytes per second. Let's record this. So with X mic AVX512, compiler is now tuning for Night's Landing, and I'm getting something like 66 gigabytes per second. And the same command to run in high bandwidth memory gives me looks like around 400 gigabytes per second. But you can see that there is a lot of variability in my results. Well, that's a good improvement, but let's think of what this variability means. Variability in this case is caused by the fact that this bandwidth is very high. Because the bandwidth is high, that each test only takes 800 microseconds. 800 microseconds is a relatively short time, even in the context of the time scales of OpenMP and thread context switching. So I would like to run my test a little longer. And to do that, I will use a built-in preprocessor macro in Stream that controls the problem size. So the macro stream array size, which is an integer in the code, determines the size of arrays that Stream uses for testing. I will set it to the highest value that doesn't result in an integer overflow, 64 million. And that should give me a slight improvement. There is almost no detectable change in on-platform memory. I still get something like 67 gigabytes per second. Let's see what happens in on-package memory. Looks like a slight improvement and looks like a little bit less of variability in results, something like 405 gigabytes per second. And let's take one more critical look at the output. There is a lot of information in the output. One interesting piece that I spot is this. Number of threads requested and counted is 256. Why 256? Remember that I have a 64-core processor, and each core presents itself as 4 logical processors, so I have 256 logical CPUs. By default, OpenMP uses number of threads equal to number of logical processors. However, bandwidth-sensitive applications prefer to have fewer threads than you have logical processors, around 1 thread per core. There are two ways to make OpenMP use 1 thread per core. The first method is based on the OpenMP standard. I would have to set something like OMP num threads equals 64. This will work, but it is now platform dependent. Because if I have a processor with 72 cores, I will have to change this number to 72 for optimal bandwidth. So I will show you one more method, which only works for Intel OpenMP, and only for the Xeon Phi architecture. There is a variable, KMP, hardware subset, which allows you to set a certain number of threads for execution per core and a certain number of cores. So the syntax is the number of cores followed by C, and the number of threads per core followed by T. And actually the first argument is optional, so I can remove this and just set 1 for threads. So I'm requesting 1 thread per core. And OpenMP will count threads itself, and it will set as many threads for my parallel loops as I have physical cores, and 1 thread per core. So let's see what that does. So when I run Stream, now you can see that it runs with 64 threads, and in standard memory it achieves something like 70 megabytes per second. So KMP hardware subset 1T, 70 gigabytes per second, slight improvement. And we will also see an improvement in high bandwidth memory. So this is the command to put my application in high bandwidth memory. And here is my expected performance. (446 gigabytes per second it looks like, and very little variability from run to run. Well, we did not achieve over 90 gigabytes per second on the in the on-platform memory because of the specifics of this of these memory modules. It looks different with different memory modules, but the on-package memory, which is fused onto the chip, performs as expected. So what we had to do is compile the code with a flag that tunes for the Knights Landing architecture. Make sure that the problem size is large enough so that we don't have a lot of variability, and also tune the number of threads for bandwidth, and that requires setting 1 thread per core. In some ways, programming Xeon Phi processors is easier than programming other Intel architecture processors, because if you try to repeat this test on a Xeon CPU, you would also find that you need to set affinity to bind software threads to cores. There is a Colfax research publication that you can read about it, but this is a pretty well-known fact that setting thread affinity in such a way that threads don't migrate improves the bandwidth of memory-sensitive applications. If you try to tune affinity on first-generation Xeon Phi processor based on KNC, you would possibly also need to tune prefetching with certain compiler arguments. And there is a white paper describing it. Essentially, for Knight's Corner, in addition to the flags that we already used, you will use at least this flag, qopt prefetch distance. If you have an application that is sensitive to memory bandwidth and you're trying to tune it, well, see if you can extract the same bandwidth out of it as stream using the methods useful for tuning the stream benchmark. And in addition, you may need to pay attention to parallel first touch and to the usage of streaming stores. And these links are clickable in the slides, and you can download the slides and click the links to get more information. As a reminder, we used NumaCTL membind to run my the application in high bandwidth memory. In principle, at this point, I've demonstrated everything that I was planning, but here is a few minutes of bonus material. Let's see. I will use the memkind library to demonstrate what I need to do to run this application in on-platform memory, selectively allocate some data structures in high bandwidth memory, and then extract bandwidth here. To do that, I will need to edit the source code of the stream benchmark. In the stream benchmark, the arrays on which I am operating are declared as global variables. I'm scrolling down to find these variables. Here they are. My goal is to modify this program in such a way that the main application runs in on-platform memory, but we will put A, B, and C in high bandwidth memory using HBWmalloc, the special allocator that allows you to selectively put objects in high bandwidth memory. I will do it like this. I will declare arrays A, B, and C as pointer-based global arrays, but then I will go down to the main function, and in the main function I will allocate arrays A, B, and C using HBWmalloc. So right here I will put A equals double, and HBWmalloc is the function, and the size of the array is the size of double times stream array size. And I will do the same for B and C. Well, if I want to be nice, I also need to go to the end of main, and then I will deallocate these arrays. Let's see where main ends. Probably easier to find it from the top. There we go. So here I will HBW free A and also B and C. So let's compile with memkind. Memkind is the library that gives you access to the HBWmalloc allocator. So if I try to just compile like this, I will get undefined references to HBWmalloc. And that's not surprising, because I forgot to include the header file and the link argument. So back to the drawing board. And before I start using HBWmalloc, I need to include HBWmalloc.c .h. And when I compile, I need to use the flag L memkind. Now the code compiles, and when I run it, I don't have to use nomoctl, because the application will run mainly in on-platform memory, but selectively arrays A, B, and C will go to high bandwidth memory. And it looks like it almost worked. I'm getting 300 megabytes per second, so definitely I am not in the on-platform memory. Let's record this. But I experienced some performance degradation from the previous result. This is not a trivial issue, and that forum thread that I had a link about in my slides explains what is happening here. What is happening is that loops in the stream benchmark now have assumed vector dependence. And to override this assumed vector dependence, I need to tell the compiler that pointer-based arrays A, B, and C are not overlapping. There are several ways to do that. I will use a method with the restrict qualifier. So here are my arrays A, B, and C. I will change their declaration slightly. A is now a restricted pointer to double precision numbers. If I want this code to compile, I have to add -restrict to my compilation flags, and now I expect good performance. Yes, and indeed when I run, I observe 437, 439 gigabytes per second. I will call this optimization step pointer disambiguation, and I achieved it with the restrict qualifier. And this gives me 438 gigabytes per second. This is the thread discussion that explains what just happened and why this is needed. In this session we talked about memory bandwidth optimization. Stay tuned for more hands-on demonstrations. I will demonstrate how AVX512 works in part 2 and give you pointers to additional learning resources, particularly to some exercises that you can run on Xeon Phi processors. So stay tuned.